we've talked here and there about interpretations of the derivative, how it tells us the slope of the tangent line and rate of change and all that. In this section, though, we're really going to focus in on that idea. That's really all I want to accomplish here in this section, is to cement our understanding of the derivative and what it tells us as a rate of change, particularly when it comes to position and kind of what we can gain from looking at the derivative. So we're not learning any new derivative rules or properties, anything like that. We are solely focused on interpretation of the derivative. So most of the time in this section, we're going to be working with a position function, s equals f of t. The average rate of change of an object over some time interval a, b, is given by f of b minus f of a over b minus a. This is not a new formula. This is just the slope formula. We talked about this way back in 2.1. We gave this actually as the average rate of change formula. So nothing really new here, but I just want to bring this back to the forefront here because I want to look at average rate of change through the lens of position. So because s represents a position function, when we talk about average rate of change, the rate of change of position is velocity. So the average rate of change can be interpreted as the average velocity of your object over this time interval a to b. And if I wanted to look at this graphically, this also represents the slope of the secant line, and we'll see that coming up in our first example here. So these three values all refer to the same quantity. They're all referring to this f of b minus f of a over b minus a, but they're all slightly different variations of that interpretation. They're kind of looking at that quantity through a different lens. And so I want to just really hit home that we're talking about the same, they're all referring to this same value. It's just different ways to interpret that same value. But we're interested really in derivatives, and we haven't talked about that yet. Remember that derivatives tell us instead instantaneous velocity is given by the derivative at a f prime of a. So if I want to talk about instantaneous velocity rather than average velocity, we use the derivative. And we'll talk more about this distinction in just a little bit here. The instantaneous velocity also represents the slope of the tangent line to f of t at some point a comma f of a. So just kind of cementing and hopefully re-establishing this relationship between instantaneous velocity or instantaneous rate of change and the slope of the tangent line and the derivative. All three of these are very much related. They're all, again, here we're all talking about the same thing. Now we're talking about the derivative. So these three things we're talking about: average rate of change, we're talking about slope of the secant line, versus instantaneous velocity, the derivative, slope of the tangent line. These three things are talking about something else, but these specific three things right here, these are all referring to the derivative. So let's look at an example here, see if we can't establish and hopefully better understand the difference between average rate of change or average velocity or slope of the secant line versus instantaneous velocity or slope of the tangent line. Let's see if we can kind of identify the difference between those two things. So here I have a figure. It shows the position of an airliner on an out and back trip from Seattle to Minneapolis, where s equals f of t is the number of ground miles. So this is the number of ground miles from Seattle t hours after takeoff at 6 o'clock a.m. The plane returns to Seattle 8.5 hours later at 2:30 p.m. Part A says calculate the average velocity of the airliner during the first hour and a half of the trip. So, okay, I want the average velocity. Average velocity, remember that is really referring to the same quantity as average rate of change. I'm thinking about f of b minus f of a divided by b minus a. So when I talk about the average velocity over the first hour and a half, So the first hour and a half, that makes me think I'm starting here at 0, 0, and I think it'll be helpful if we label these points. So we have this point here at 0, 0, and then at an hour and a half, I will have to estimate, but it looks like right around here I've got 1.5, comma, looks like 600. So these are 2 points, and I want to find the average velocity, or I can think of it as the slope of the secant line connecting those 2 points. So I think I'll call this guy over here, I'll call this b, comma, f of b. And over here I've got a, comma, f of a. And I don't even need to plug things into my function because I actually already have the y values, which is good. It's less work for me to do. So if I try to use this formula f of b minus f of a over b minus a, f of b, that's 600, minus f of a, that's 0, divided by b, 1.5, minus a is 0. So I just have 600 divided by 1.5, which should give me 400. And we're talking about average velocity, so I would like to give a unit here. My unit of position, miles from Seattle, so 400 miles per unit of time per hour. So our average velocity here in this case is 400 miles per hour. So there is our average velocity. So we picked 2 points on our graph right here, and we found the slope of that secant line that connects those 2 points. That's really all we did here. Part B, this is asking a slightly different question, but we're still talking about velocity. It says, at what times is the velocity 0? Give a plausible explanation. So what times is the velocity 0? Now notice we just said the velocity. Notice more importantly what we didn't say. We didn't say average velocity. When we simply say velocity, what we really mean is instantaneous velocity. Instantaneous velocity. So if we just see velocity, or even if we just say rate of change, we're always talking about the instantaneous velocity or the instantaneous rate of change. So I want to know, where is the instantaneous velocity 0? So okay, instantaneous velocity, that makes me think of the derivative. We're talking about f prime of x, or s prime, whatever. Well, this is f, so f prime of t, I suppose. I should probably use the correct variable here. F prime of t. Where is that? 0. So where is f prime of t equal to 0? Well, what would I see with this graphically? When f prime of t is equal to 0, we've kind of gone the other way. If f prime of t equals to 0, remember f prime, this is the derivative, that tells me, this piece right here tells me slope of the tangent line. So I want to identify x values, or in this case t values, where the slope of the tangent line is equal to 0. Well, what would it look like if I had a tangent, a tangent line with a slope of 0? Remember, if I have a slope of 0, we're talking about a horizontal line. So another way I could phrase this question is I could say, hey, where do I have a horizontal tangent line? So where do I have a horizontal tangent line? And if you look, most of the other problems we've looked at, we started by saying, go find the x values where we have a horizontal tangent line, and we have to use this formula. Here we actually went the other way. We said, okay, we're going to start with this, and then, okay, well, what's that look like? It looks like a horizontal tangent line. So let's look at our graph, and let me erase some of this just so that we can clean it up here. So if I pick a number kind of on that left side of the graph, if I draw in a tangent line, let's just pick right here. If I were to sketch in the tangent line right there, I look at the slope of that line. That line is increasing, so the slope is positive, which means the velocity is positive. Well, that's not what I want, and I could pick other points, right? I could even pick this point right here. If I sketched in the tangent line again, well, it's still positive, the slope of that line. So that's not what I want. If I pick a number on the left-hand side, and this works for any number, I'm just going to pick right here. If I were to sketch in the slope of, or excuse me, if I was to sketch in the tangent line and ask myself, what's the slope of that line? The slope of that line is negative. Well, that's not what I want either. Remember, I want the derivative to be 0. I want the velocity to be 0. So, okay, that's not it. And again, you can pick any point on that left-hand side, right? You can look at this point right here. I have a negative slope, which means that my velocity is negative. It's only in this middle section right here where I actually do have a horizontal section where I have that horizontal tangent line. So if I was to sketch in the tangent line, it looks like anywhere between t equals 3 and t equals 5 if I have to estimate. That's where I have that velocity of 0. So at what times is the velocity equal to 0? I don't want to worry about exact times. I'm just going to say between t equals 3 and t equals 5. So between these two t values, that's where I have a velocity of 0, because that's where the slope of the tangent line is 0, because slope of the tangent line and velocity are really talking about the same thing. Those values are the same there between 3 and 5. The other part this problem asked me to do, so let me clean this up here just a little bit. We also want to talk about a plausible explanation. What does that look like? So a plausible explanation, so I want to kind of go back and revisit the prompt for this problem. It says we have an airliner that's on an out and back trip from Seattle to Minneapolis, where S equals f of t is the number of ground miles from Seattle t hours after takeoff. So if I think about what happened, my plane took off from Seattle, it landed in Minneapolis, and then it flew back. So I have this gap right here. What's the logical explanation for happening right there? So what I think happened is between 1 and 3, or between 0 and 3, excuse me, look at what's happening to the distance between, because this is the distance that my plane is from Seattle. The distance is increasing. So I'm flying to Minneapolis right here. And then what happens here? Well, I end up at Minneapolis. I stop there. Then afterwards, I'm flying back. So the distance between the plane and Seattle is decreasing. It's getting smaller and smaller. So it's this distance right here. What's going on there? Well, my plane landed in Minneapolis. So if I want to talk about a plausible explanation, you could say, well, the plane landed in Minneapolis. Perhaps it's just sitting on the tarmac waiting to take off, or perhaps they're waiting for passengers that are on the plane to get off and then new passengers to board so that they can fly back to Seattle. Maybe they're changing crew out, or they're refueling, or there's a number of explanations that we could give here. Any of them would do. But as long as you're interpreting this section as, okay, that's a time when we're just kind of on the ground, where the plane's not really going anywhere. If the velocity is 0, that just means the plane is staying exactly where it is. So as long as we have something along those lines, that's what I'm looking for. Part C says determine the velocity of the airliner at noon and explain why the velocity is negative. So we want to look when t equals 6. So let's go to our graph here. Let's erase it and clean it up here. So at t equals 6, we're talking about this point on our graph. And again, notice it says determine the velocity. It's not average velocity, just the velocity. So we really want the instantaneous velocity. Instantaneous velocity, that means derivative. That means I want the slope of the tangent line. So let's sketch in the tangent line. Let's see if I can give an idea at least of what it looks like. Let's see. Probably won't be perfect, and that's okay. Perhaps it looks something like this. That's probably good enough. Now, there's no way for me to really know exactly what my velocity is. because I don't have a function to work with. If I knew the function, I could take the derivative. But what I can do is I can estimate the slope of this red line that I sketched in. So I'm going to pick 2 points that are on this graph. How about this point right here? Let's estimate that point. It looks like 5, 1600, and then this point right here we have 6, 1200. Looks like. And I'm going to find the slope of the line that passes through these 2 points. So let's see. The slope formula, right? I'm still just using kind of the same formula here, and I'm actually going to come back and talk about why this is f of b minus f of a over b minus a. So let's see. I'm going to call this guy right here. How about we call this a comma f of a and b comma f of b. So let's see. I will have 6 minus, f of b. So let's see, 1200 minus 1600, 1200 minus 1600 divided by, should be 6 minus 5, yes, 6 minus 5. So 1200 minus 1600, let's see, I will have negative 400 divided by 1 gives me negative 400. So negative 400, again, we're talking about a velocity, so let's give a unit, negative 400 miles per hour. So, okay, negative 400 miles per hour. I want to address a question first that I'm anticipating that I'll receive, though. And that's, well, okay, here you said velocity, you said instantaneous velocity, but then up here we said average velocity. Why are you using the same function or the same equation in both of these two? Well, I am, you're right, I am using the same equation, but look at how I came up with these points. Over here on this red line, I picked 2 points that are on my tangent line. This red line is a tangent line. Versus that first hour and a half, if I draw that in again, that first hour and a half, I was looking at what's the slope of the secant line. So we're just talking about slope, but we're talking about slope of 2 different things. We're talking about slope of the secant line versus slope of the tangent line. Those tell us 2 different things. They tell us instantaneous velocity or average velocity. So that's why I'm using the same formula, because we're just talking about slope in each case, but we're talking about the slope of different things. So, okay, we have the velocity, and then it says, and explain why the velocity is negative. So we ended up with a negative, which is good. We were supposed to. Why is the velocity negative? Remember that this describes a rate of change. So this describes the rate of change of the miles from Seattle. So this is telling me about how my miles from Seattle is changing with respect to time. So this means if I kind of think about this in terms of, if I write this as a fraction, negative 400 miles, I'm going to say from Seattle, divided by 1 hour. When we talk about this negative right here, remember that we can use a word of change, right? Because the derivative is talking about change, increasing or decreasing. Well, if we have a negative, it's probably decreasing. What's decreasing? The number of miles from Seattle that we are. So every 1 hour, we are getting closer to Seattle. Our distance from Seattle is decreasing by 400 miles per hour. That's why. So if you wanted to just talk about why the velocity is negative, well, it's because the plane's getting closer to Seattle. And that's why the velocity is negative. So this is a really good example, I think, that hopefully illustrates the difference between average rate of change and instantaneous rate of change and slope of the secant line and slope of the tangent line. In the next video, we'll take a look at how position, velocity, speed, and acceleration are all related, and we'll look at a problem that deals with all of those things.